let everybody join. Welcome, everyone. Thank you all for being here. I'm going to spotlight us. Okay. I'm just going to add you. You're going to be hanging out with me here in the hotspot, Hakeem, while we do announcements. So
After this winter, a hot spot is good.
So welcome everyone to our last and final International Dark Sky Week celebration webinar. We are incredibly grateful and excited today to be joined by Hakeem Oluseyi, who I have been a huge fan of for years and years, and I'm so excited to finally have him join us here today to celebrate International Dark Sky Week 2025. So wherever you are calling in from, please hop in the chat and say hello and let us know where you are in the world. My name is Betty Maya Foote. I'm an engagement associate here at Dark Sky, and I am from Tucson, Arizona currently. So I have a couple announcements before we dive in, but first I just want to give a huge thanks and shout out to our community for the incredible showing of International Dark Sky Weeks. We've seen over 100 proclamations, so please give everyone a round of applause for that incredible effort. It makes such a big difference around the world, and it's been so cool to see all of them coming through from all countries, all around the world. So thank you everyone for helping spread awareness about dark skies, and proclamations are the first step towards positive ordinances to protect the night sky. We've also seen countless events and had awesome reach on social media. So I just want to truly thank everyone for their courage and bravery in protecting the night. It's really not an easy thing to do to stand up to this global environmental threat, and I'm incredibly honored to work alongside all of you every day. Thank you. So one quick announcement, if you haven't seen it yet, our home lighting assessment is up and ready and revamped. So if you're looking for an easy way to get involved and take action right now after this inspiring webinar, I'm going to pop the link in the chat, and there's simple, easy tools you can do to evaluate the lighting around your own home. And then you can submit on our form. It's just a little self-certification. So I would encourage everybody to do this tonight to celebrate the last day of International Dark Sky Week. All right, now, thank you for sticking through me with those announcements. I am excited to introduce our speaker tonight, Hakeem Oluseyi, and his talk is called Earth's Miraculous Night Sky, and I'm so excited about it. So the overview is that Earth's night sky is not just beautiful, it's a cosmic miracle. Astrophysicist Dr. Hakeem Oluseyi explores how Earth's thin atmosphere, deep magnetic core, and the sun's vast heliosphere shield life and reveal the stars. Join him on a journey through planetary science, solar physics, and cosmic discovery, and see the universe and our place within it anew. So Dr. Hakeem Oluseyi is a distinguished astrophysicist, inventor, author, and science communicator whose career has spanned the frontiers of solar physics, astrophysics, and space explorations. He earned his PhD in physics at Stanford University and has contributed to our understanding of the sun's atmosphere, solar wind phenomena, and the boundaries of our heliosphere. His semiconductor physics and astrophysical instrumentation innovations, along with his study of cosmic plasmas and the universe, have earned him 7 US patents and more than 100 scientific publications. Today, Dr. Oluseyi serves as the CEO of the Astronomical Society of the Pacific, awesome organization, if you guys haven't heard of it. I'll pop the link into their website after this. And as a public spokesperson for NASA's upcoming IMAP mission. Set to launch fall 2025, IMAP will map the outer edge of our solar system and its interaction with the galaxy beyond. A dynamic communicator known for making complex science vivid and accessible, he has shared the wonders of the cosmos with millions through his appearances on Discovery Channel, PBS, and Netflix. He is also an Emmy-nominated science journalist who explains the latest scientific breakthroughs for news organizations worldwide. Tonight, he leads us into the hidden structures that protect our world and allow us to witness the miracle of a star-filled sky. Please welcome Dr. Hakeem Oluseyi.
Thank you. Thank you, everyone. Thank you, my fellow travelers and nerds and explorers. I'm going to share my screen here. Now, the play button hid behind there we go. Yeah, so thank you. I am, as Betty Maya said, the CEO of the Astronomical Society of the Pacific. And if you're unaware, it is America's first and oldest national astronomy organization. It was founded in 1889 and it is 136 years old. So join us and let's bring the universe to everyone. And speaking of which, here's a beautiful image of the night sky. This is what we wish we could step outside and see, right? But many of us, we can't. And as I reflect on my own journey with the night sky, I think back to I was a kid and I would move every year, but it was between cities. It was between New Orleans, Houston, and Los Angeles. But then at the age of 9, for the very first time, I went to my father's homeland, his home village in rural Mississippi in the 1970s. And it was a completely different sky. It was dark and it was bright, if you know what I mean, right? The planets were just blazing through. I had no idea they were planets. And I just looked up there at the sky the same way I would look at an electronic circuit board, which was fascinating, but I have no idea what's going on there. And as I found myself traveling, I found myself on the West Coast a lot. This is as a high schooler in college. I worked at Northern Arizona University for a summer, and then I became an actual astrophysicist. And I found myself in America's darkest skies in Arizona, all over the Mountain West, in Hawaii. I found myself in the Canary Islands. I went observing down in Chile. But let me tell you, about 22 years ago, I was traveling across Eastern and Southeastern Africa from um, Lusaka, Zambia to Arusha, Tanzania. And somewhere near the border between the two countries, I found myself in a hot spring that was about 2 feet deep, staring straight up at the center of the Milky Way galaxy. And I felt like I was looking at the sky for the very first time in my life, right? And so this was the southern hemisphere. So instead of this core of the Milky Way being near the horizon, it was straight overhead. So just like in this image here, I could make out the nebulae and the star clusters, right? And the variations in brightness. And I was like, oh my God, I get it. I get why, we hear these stories of the ancients and how fascinated they were with the night sky. And, I was looking at their sky. And as I left, that had a serious impact on me. And then I began to, look into exoplanet research and I began to realize that, even though every sci-fi movie has scenes where we fly to an alien planet and you go to the planet and it has a sky, right? But I started thinking like, I'm not sure that's right because out of all the planets we found, for the most part, atmospheres come in one of two configurations: super thick or nearly completely absent, right? So, take, for example, other terrestrial worlds in our solar system, like Titan or Venus. Their clouds are so thick that if you were a being on there, I mean, aside from freezing to death and being boiled in acid, you wouldn't even know that stars exist because those atmospheres are just too thick. And if you think about where life is going to be found in the universe, NASA says follow the water. And in our solar system, we have 38 gravitationally rounded worlds. Guess how many of them are ocean worlds? More than a quarter, 10 of them are ocean worlds. So if life is where the water is, you know where the water is? Locked under miles of ice and rock. So I begin to think about how special we are here on Earth because we have this filter that allows multicellular land life like ourselves to thrive on the surface of this world. And this filter has 3 layers, right? Unless you're in the ocean, then you have 4 layers. But they are Earth's atmosphere, Earth's magnetosphere, and the sun's magnetic field that we call the heliosphere. And, I think that it's not often appreciated that, if you look at the almost, the thousands of worlds that we've now discovered with Kepler satellites, ground-based observatories, test satellite, most of them are not terrestrial worlds, right? They're worlds that are encased in these thick atmospheres. But here we are with this thin sliver of an atmosphere. You might think, well, what about Mars? Well, Mars's atmosphere is so slight that radiation from the sun penetrates 2 meters into the ground, over 6 feet into the ground. So it doesn't have a strong magnetic field either. And I'll get to that in a second. But, how fortunate we are to have this shield that lets the good stuff in, but keeps the bad stuff out. So what's the good stuff? Light. Light arrives on the surface of our planet through an atmosphere. That's rare, right? That's not really happening in many places. And so if you look at the history of life on Earth, as early as we could potentially find life on Earth, and even earlier, there's evidence of life on Earth getting started incredibly quickly, right? Like 4.2 billion years, 300 million years after the Earth formed. Kind of like James Webb is discovering galaxies form around 300 million years after the universe formed. But in any case, what happens here is that light was bathed in abundant life. So when you look at the first conclusive evidence of life, and it's these stromatolites, right? They are photosynthesizing stromatolites, right? These photosynthesizing single cell organisms. And it still took, another 2.5, 3 billion years for oxygen producing photosynthesis to come about. And that oxygen is what allows our multicellularity. And so what makes Earth different is not that it has water, but that it lets this light in to power oxygen to produce in photosynthesis, which can then power multicellular life forms like ourselves. So our Earth's magnetic field is the second, going out from us from the surface. The Earth's magnetic field is the second layer of this filter. You have to protect yourself from the sun. It gives us the energy, but it's also pumping out a lot of protons and radiations and magnetic fields. And so the magnetic field of Earth is what protects us from the sun's magnetic field. So here, for example, is an animation of a pretty regular occurrence, which is there's what's known as a solar storm, and that solar storm carries with it magnetic fields and plasmas that apply a pressure to our magnetosphere. These are our magnetic fields, and it causes them to reconnect. And changing magnetic fields create electric fields, right? That's how induction works. How you charge your how you charge, you can charge things without actually plugging something into another, right? You just set it on top of it because you have the fields changing, creates currents, which can then charge a battery, but it could also create currents in your magnetosphere where it can enter at the poles. But without our magnetic field, things will be much worse for us. So why do we have a magnetic field? Because Venus doesn't have a strong magnetic field. It's terrestrial. It's about the same size as Earth. Mars does not have a magnetic field. Mars is, about half the size of Earth, but it's also terrestrial. And unlike Venus, which takes about 270 days to make one rotation, Mars also spins at about 24 hours in a day. And that's relevant because we know magnetic fields are created from moving electric charges, right? Electric currents are what moving electric charges are, and currents create magnetic fields. So when you think about an electron's magnetic field, the model that we have that's spinning, even though it really isn't. Or the atoms that have magnetic fields, like a bar magnet, right? Those are those magnetic moments of those electrons orbiting, all adding up in one direction. And so inside of our Earth, we have flows of liquid metal. We have currents. And this is like so underappreciated, if you ask me, but this is mind-boggling to me. If you look at the structure of our Earth, the internal structure, you can think of it in fifths. The inner 1/5 of the radius is a solid core that's slowly growing by atoms in the liquid outer core, that next layer sticking to them. But then the next 2/5 are liquid. Like, do you think of the ground underneath your feet that way? The core, 2/5 of the interior of the Earth is liquid like that. That's mind boggling to me, liquid metal. And then you have the mantle, which is solid, the last 2/5 roughly, but it's a flowing solid. But the point is that inside that liquid metal core, there are what are known as convective currents. Convection is like what happens when you boil water. Heat rises. The flow of energy goes from inside to out, but it's turbulent, right? It's this turbulent flow. And so you have Earth rotating fast at 24 hours in a day. And then you have these currents inside that liquid metal core, and that creates our giant magnetic field. But here's the thing. Here's an image of what that looks like. And it's weird. It can flip, right? And it has many times. We see that in the geological data. But also, if you think about Venus and Mars, why don't they have strong magnetic fields? And Earth does. Well, again, it's another miracle, just like our thin atmosphere that is sufficiently substantial to provide some shielding, thin enough to let light in, but sufficiently substantial to provide radiation shielding. Earth was struck by a Mars-sized object early in its formation called Theia. So if you think about what happens when a terrestrial planetary body forms, first, they form from accretion. That means to grow via collisions. And if you're sufficiently massive, you can become gravitationally rounded. You can melt due to the energy of the collisions, due to the decay of radioactive elements. And then you will have a layering and a stratification where the denser materials will sink to the center and the lighter ones will rise. But on Earth, as it was in the process of doing that, here comes Theo and just disrupts the entire thing. And it's believed that that collision, in addition to forming the moon, is what allowed our core to remix and not do what Venus's core has done, which is basically, it has a partial molten core, but it's stratified and layered in that way that I described. And Venus is rotating really slowly, but it didn't have those convective currents set up. And so that allowed heat to flow out from the interior of the Earth, and it also allowed um, uh, what is that movement of the continents called again?
Oh,
It
continental
escapes.
drift.
Yeah, plate tectonics. That, yes, yes. It allowed plate tectonics to occur. So here now, no collision, we don't have our strong magnetic field protecting life here on Earth, which is, again, just wild to me. Another thing that's kind of pretty interesting that I find is that, the moon is about half the size of Mars, which means it's one-fourth the size of Earth, but it's only 1% the mass of Earth, right? So you can think of Mars as like, I mean, the moon is like a fluff ball of Earth mantle. It doesn't have that big metal core. So Thea's core and the Earth's core mixed and stayed inside of Earth, and the moon ended up being, a fluff ball. Uh, it's not a fluff ball, but you can make it that way if you think about it like that. Um, so now we're inside of the sun's protective heliosphere. This is the sun's magnetic field. And the thing about the sun is that it's not a solid terrestrial body like the Earth is. So, or the other planets that I mentioned. And so it's made of plasma. So that means that things are going to get a lot more complex. And one of the things that the sun has, due to the action of its magnetic fields, uh, primarily is what we call a solar wind. And so the sun is blowing material out. And, that material is some of the material that could have, that does strip away our atmosphere, has stripped away the atmosphere of Mars, has stripped away some of Venus's atmosphere to create an ionosphere around it. But it also puts a pressure on space, right? So the sun isn't alone. It's in this massive system of hundreds of thousands of stars that includes, exploding stars, colliding dead stars like neutron stars, black holes, white dwarfs, black holes that are voraciously eating, their partner star or from an accretion disk. And what that means is it is an incredibly violent radiation environment out in intergalactic space, out in interstellar space, excuse me, the space between the stars within a galaxy. So we need protection from all of that. And as you see right here, the interstellar wind is essentially the flow of that radiation, ions primarily, right? Protons, a lot of protons, electrons, and some heavier ions, oxygen, neon, those sorts of things. Um, they're directed around our solar system instead of penetrating deeply within. Okay. And the sun is moving. So here again is how the sun creates its magnetic field. So we talked about two main motions with the Earth. You had the rotation, the global rotation 24 hours a day. Then you had the turbulent convective currents in a liquid iron core. Well, the way the sun works, when you think about a star, I like to think about a star as being two parts. One part is the core that creates the energy that flows out, and the other part is the envelope. And that's what's crushing down on that core to maintain its temperature and pressure and drive those interactions, those reactions in the core. But also, the envelope must respond to what the core is doing, right? The core, as the star ages, the core gets smaller, more dense, and hotter. It increases its energy output, and in response, the envelope swells, right? And causes the surface to cool as it grows into a red giant. But what's important is how the energy goes from the core outward to the surface of the star. So in different stars, based on their mass, it works differently. So from the sun, the inner third, by the way, half of the star's mass is in the core, which occupies about the inner third of the radius. All right. The other half is in the envelope. And what happens is the energy can leave in one of two ways. One is what we call convection. A parcel of mass, a volume of mass moves upward. But as it moves upward, the pressure drops. So that means it'll expand. And if you expand the gas, it cools. So as it starts expanding and cooling, the question is it still hotter than the surrounding material? And if it is, that means that process of moving the material upwards is more efficient than an alternative process. And so where that remains true, you have what is called a convective flow. The outer third radius of the sun is doing that convective flow. Interior to that, you have what is known as the radiative zone. There, if a parcel of gas rises and expands, it's cooler than the surrounding material, so it sinks again. So that doesn't get energy out. So it's only by, as the light energy is coming in, it strikes something, and that thing absorbs that energy, moves around, and it re-emits it in a random direction. And slowly, photons created in the center, their energy leaves the surface of the sun tens of thousands of years later, right, through this process. But the point is that the sun has a global rotation that's weird because it rotates fastest at the equator and slowest at the pole. So at the equator, it rotates at 4,400 miles per hour. And at the pole, the rotation is 1,000 miles per hour slower. And what that means is it takes the pole about an extra week and a half to make one rotation as compared to the equator. So you have a differential global rotation. You have convection north-south, but then in a thin layer near the top, you have what's known as I'm going to mispronounce it. It's one of these words that I only see in print, so I don't know. It's based off meridian, but it's meridional or something like that. So the speed of the global rotation is something like 16,000 miles per hour. The speed of 4,000 miles per hour. The speed of the meridional flow is like 40 miles per hour. All right, it's like 100 times less, but it's key in the creation of the sun's magnetic field. And as it gets near the top, these flows break up into little cells. And so you get all these kind of weird structures with magnetic fields emerging from the surface of the sun, containing energy wound up in them where they heat the plasma to millions of degrees, creating the sun's corona like an image that you see here. And this is where I started my career. So let's go all the way back to the 1990s. You see that incredibly good looking guy there? No, not him. The other incredible, no, not, yes, that one. That's me. If you watch Ancient Aliens, don't self-identify. The dude in the white jacket, Richard Hoover, he's always there. The guy in the center, that's the late, great Dr. Arthur Bertram Cuthbert Walker II, ABC Walker. He passed away, but he was my PhD advisor. And so the guy in the Touching the Rocket, Dennis Martinez, he's at Stanford Linear Accelerator. The guy with the black hat on, Charles Kankelborg, he's a professor at Montana State and the principal investigator for the Moses rocket. That guy, Dave Gore, I don't know where he is these days. But yeah, we were flying our rocket, and here's what our data looked like, right? So we were the first to get these full disk images of the sun in extreme ultraviolet and coronal lines. And this is what it looks like today, right? It became the standard in the field. And I'll tell you what's really interesting is, what had happened is it was the development of a new optics technology that we applied to astrophysics. And while we were working on this, I was in Silicon Valley. I went to graduate school in Silicon Valley. And the people in the lab would say, oh, yeah, this is going to be used for EUV lithography in the future. I had no idea what that meant. I would hear the word lithography all the time. And even though I'm not shy about my ignorance, I'll say in a second, I don't understand that word. For some reason, I felt like I should know the word lithography. And this is pre-internet up today and mobile phones. I could have just looked it up. But here's the wild thing. It did eventually come about. EUV lithography. It took a long time, right? This work began in the late 80s. It came about in the 2000s. Guess how much one EUV lithography machine costs? They're sold by this one company in the Netherlands. One machine costs $1.5 billion. That is unbelievable. So when we look at the sun's atmosphere on the large scale, right? We look at the shield that it provides us so that we can be here, stand here to look out and know that there is a universe out there and know that there is a galaxy. Because this pressure from the solar wind, and there's two types of solar wind. There's three types. There's the main solar wind, which comes from mid-latitudes and equatorial regions away from the poles, and it flows out at about 1,000,000 miles per hour. And out of the poles and areas that are called coronal holes, you get high-speed solar winds, and they're twice as fast at 2,000,000 miles per hour. And then there are these episodic winds, which I know the number in kilometers per second, which is like 3,000 kilometers per second, but it translates to 1% the speed of light, right? So when you have a big flare or jets, you get that material going out. But essentially what happens is that material that's flowing outward from the sun blows out a bubble and it goes supersonic. It flows out subsonic, crosses a singularity of sorts, goes supersonic, and then at a certain point, the pressure of the solar wind falls off sufficiently because it has to cover a bigger and bigger sphere that it equals the pressure of the interstellar medium, the space between stars. And at that point, that's where the boundary between the heliosphere and interstellar space is. So it's just like this, right? So if you look at this flow, if you ever done this experiment in the sink, that flat area immediately around the where the flow hits the sink, where it says fast flow, that's the supersonic region. But then as it goes out, you end up at this turbulent boundary, which we call the termination shock. And then there's this transition region that's really turbulent, and then it goes out into the smooth flow again, right? And so our structure is just like that, right? So you have the termination shock, and then you have that turbulent region in there, and then you have where you match up with the outer flow at the heliopause. Now, where you see bow wave, just like a ship moving through the ocean, if it's moving slower than the speed of sound through water, then the pressure signal goes out in front of the ship, and the water knows to kind of spread out, right? And so the ship passes through. But if you go faster than the speed of sound, faster than the pressure wave can propagate, then the water ahead of you don't know you're coming, right? You build up what's called a shock. So supersonic airplanes do that. Before it was measured by the satellite called IBEX, people thought that there was a bow shock in front of our solar system. Turns out there's not. There's only a bow wave. So if you go online and you look up images of the heliosphere, you'll see a lot of them labeled bow shock out there. But that has been shown to not be the case. It's what we expected, but it's not the case. So how far are we talking out, right? Where this termination shock occurs. It's almost 100 times the Earth-Sun distance away from us, all right? And if you look at the structure of our solar system, the Oort cloud is this region of cometary bodies, right? You have the flat plane of the Kuiper Belt where Pluto and its family lives. And then outside of that, you have a spherical cloud. And that's sort of the remnant of the giant molecular cloud from which our solar system formed, right? It was even bigger than that, this core. But the inside came down to a disk and then it spreads out and then it becomes a sphere around us. And so that goes out about 100,000 times the Earth-Sun distance. And We have sent probes out there, the Voyager 1 and Voyager 2 probes. They've gone beyond the heliopause and out into interstellar space and sent back signals. But this is the new satellite, the IMAP satellite, that is um, going to be launched this fall by NASA. I'm the spokesperson for the satellite. It's the follow up to a precursor satellite called IBEX. And IBEX did a very interesting, this is what IMAP looks like now. This is what it, well, not today. This is like probably a few years ago. This is because the instruments aren't in there, maybe last year. But this is what the spacecraft looks like. So what's going on? Outside in those magnetic fields that surround Earth, that surround the sun, charged particles are trapped in those magnetic fields. So here's what happens. If, say, for instance, my arm here is a magnetic field. If a particle carrying electric charge, like a oxygen atom that's missing a couple of electrons, is going to have a mismatch between the number of protons in the nucleus and the number of electrons surrounding. So that means that those charges aren't going to be canceled, right? If you have one-to-one match, it's canceled and it's a neutral atom. But if you're missing a few electrons, now it's what we call an ion, right? And so ions, because they have that electric charge, they experience something known as the Lorentz force. So the Lorentz force is given by the charge versus the speed versus the strength of the magnetic field. And it works perpendicular to the direction of the magnetic field and the direction of motion, right? So it's going to push it that way. And so the particle is forced to orbit that magnetic field. But remember, there are ions flowing outward from the sun. And on occasion, one of those ions will collide with one of those atoms, a hydrogen atom, say, comes from the sun, not an ion, an atom, and it collides with one of the ions trapped in the magnetic field. And the ion captures the electron away from the atom. So now they switch places. The atom that was flowing inward from the solar system was free. It was electrically neutral. It was ignoring magnetic fields. But then once it gave its electron away to that ion, now the ion is neutral. So it's free. And it'll fly off in some random direction, whereas the atom now is now an ion. It gets trapped in the magnetic field. So some fraction of those neutral atoms will stream into the inner solar system. And IBEX, the IBEX satellite, found them and measured them across the entire sky and found something no one expected. And this is that red and green area in the middle is known as the IBEX ribbon. And the blue stuff around it is what's called the global distributed flux. So that's just like the mean number of neutral atoms flying in. And then that is where there's an intensity enhancement. And what's interesting is that if you look at these lines here, this is the galactic magnetic field as it wraps around our solar system. And you see that the IBEX ribbon is perpendicular to the galaxy's magnetic field. And you also notice that where Voyager 1 and Voyager 2 crossed the heliopause to come into interstellar space, it went around the IBEX ribbon. So the Voyagers could have discovered this region of enhanced stuff in the magnetic field there, but they missed it. But IBEX found it. So the IMAP satellite is the follow-up. And this is what really is a simulation of what our complex magnetosphere inside of the galactic magnetic field looks like in 3D. Now, you got to be really tall to get that view. That's humor. That's my attempt at humor. But, look, we have this miracle night sky, and we ourselves are miracles, right? I love to study deep history, and I love to study human evolution. And I think of us as, those little, hard knock life Australopithecines, right? Homo habilis breaking a rock and realizing that they can, scrape off meat more efficiently from a carcass. And now we realize now this is a simulation from Sloan Digital Sky Survey data of the 500,000 nearest galaxies. And we've been able to figure out all of this, right? Our magnetic field is invisible. It was first discovered by William Gilbert and published the book The Magnet in 1600, right? And for reference, that's between Copernicus and Newton, right? That one of the earliest scientific treatises was when they realized that the Earth is a magnet in 1600. Well, the sun's magnetic field wasn't discovered till 1908. It took another 300 years. And at this time that the sun's magnetic field is discovered, we don't even know that there's another galaxy in the universe. And now here we know that we live in this universe that's populated by hundreds of billions of galaxies. And by the way, I did a little calculation, and I wanted to come up with a visual model of how galaxies are spread out in the universe that was relatable. And so it turns out that galaxies are separated from each other. So this is pretty wild. If you look at the atoms in your body, right, the cores of the nuclei, which of the atoms, which is where most of the mass is concentrated by far, are about a few 100,000 times their own size apart from each other, right? So you're mostly empty space. If you look at a galaxy, the stars, right, are light seconds across, but light years apart, right? So they're tens of millions of times their own size apart from each other. So how far apart from each other do you expect galaxies to be in terms of their own size? Some super big number? That's what I guessed back when I guessed. But it turns out that they're like 10 times, right? The Andromeda galaxy is like 13 Milky Ways away. Galaxies are really close. And you know what else is about 10 or 100 times their own size apart from each other? Air molecules. So to picture the universe of galaxies, picture air molecules. And so we estimate that there's something like, several hundred billion galaxies in the observable universe. That's like a cubic millimeter of air. So that's your model of our universe, a cubic millimeter of air. But yet here we are with our imaginations and our technologies and our ability to look up and see that there is a sky there and there is a universe out there, that this little ape that broke a rock is now building satellites and putting the whole picture together from the inside out. Man, I tell you, I see myself in this big story of life. A few last month or so, I got my family tree, and I looked at those names back to 1700. I'm like, darn, I'm just a name in there too, right? Only just that future isn't quite there yet, right? But we are determinative in some sense of that future. And the future that we are leaving our children, we have some control over, right? And so here we are as nerds with this an appreciation of this amazing cosmos that we live in, and it's up to us to preserve it. And those of you who, it's possible. That's the thing, right? Yeah, we're going to turn off all the lights on Earth, make them downward looking, but then we're going to look up and there's going to be all these streaks from satellites. Not calling no names, but, preserving the night sky for both the naked eye and telescopes, I think, is one of these things that does not immediately provide a benefit, right? The stuff we do when it goes up against medicine and saving lives, people weigh in and say, oh, why should we do this when we can do that? But it's not a trade-off. And as humans, we're more than just surviving, right? We are poetic, and we are, we through inspiration we achieve even more, right? And what is more inspiring than the universe in which we live? And we should preserve it for future generations to see. Thank you. Any questions, as we say in Mississippi?
Well, thank you so much, Dr. Oluseyi. That was incredible and very inspiring. And man, am I gonna need to watch that again?
Did I go too fast? We talk fast in Mississippi.
No, that was amazing. Yeah, a lot of incredible information, and I really am looking forward to watching it again. And when I'm not like worried about people unmuting themselves, so that I can really dig into that, because that was incredible. And I absolutely loved your quote. We have a miracle night sky and we are a miracle. And I think that this network of dark sky people really appreciate that. And that's one thing that I love so much about the dark sky community, is that we care both about the night sky and about the people and the planet and all of us together as one cohesive universe. So thank you for saying that so beautifully and sharing all of your incredible information and work with us today. So there are some questions in the chat, but I'm going
All
to
right.
start with kind of just a basic question. Because it is Dark Sky Week and we are
Yeah.
celebrating, I would just love to hear from you kind of what you love the most about dark skies and night skies.
Oh man. When I think about night skies, literally I think about standing outside and talking to people. So we're in this world of mobile phones. and I, and, you know, I was telling my son, was like, I was like, yeah, we used to just do that. We would just stand outside and talk. But I lived in rural America, and I remember that trip where I was telling you in Africa, there was this graduate student. He's passed away from cancer. His name is Alex Tung. And if you Google his name, when he was first diagnosed, he put his story on the internet immediately. And it was, he was this is before people were doing that. This is around 2005. But Alex and I would sit up every night, and he was just quizzing me about both the university and graduate school. He was attending the same graduate school, but he was in engineering. I was in physics, and that's what I feel like. It's like when people ask me, I've traveled a lot, I've been to 44 countries, and people ask me, what's your favorite country? It's hard for me to answer because I just fall in love with humanity everywhere I go, right?
Amen. Yeah.
Yeah. And I just want to get in with people. And so for me, it's a shared experience, right? But I'll tell you another night sky night that really blew me away. This happened in the 90s. And so I remember my PhD advisor, Art Walker, he goes, what's the solar um radiation output 10 to the 30 ergs per second? Was it 10 to the 30? And I'm like, beats me. I'm a young graduate student. He goes, what? You call yourself a solar physicist? Which I did not. I should have been thinking that way, but I wasn't. I was suffering from what's that called? Oh,
Imposter syndrome. We
yeah,
all got
imposter
it.
syndrome. Yeah, y'all are
Yeah.
solar physicists. I'm just trying to get in where I fit in. Um, but man, that was like, dude, I need to have these numbers in my head. So I started like putting the numbers, Texas Hill Country, right, right on. I used to I started putting those numbers in my head of the sizes of everything relative to everything else, the distance of everything relative to everything else. And so I would teach observational astronomy up at the observatory. And one night, and sometimes after class, I just decompressed by standing outside and looking up at the sky. And man, I was doing that one night and it went 3D on me. I could see the sky in 3D. And I'm telling you, it was like, vroom. It was kind of like, I can think of moments like that in my life. Like I remember when I went to Egypt and saw the pyramids, like, vroom, like you're just shook, right? And it was like,
Yeah.
whoa, right? Yeah.
Yeah. I agree. Like those moments of for me that are the most poignant are like, yeah, when it feels like the rug's been pulled out from under me and I like don't have a reference anymore or a place to stand and feel like part of this larger universe. So yeah, I totally understand that. There are some questions. Janet S says, very inspirational and a privilege to be here. I agree, Janet. Janet asks, what would you like to see more of from biologists to support dark sky initiatives, as there are so
Ooh.
many overlaps with habitat conservation and this work?
Oh, that is so good. That is so good. Yeah, that is a really good perspective. We can work together. Um, I used to live on the east coast of Florida, right? And so there were light regulations that had to do with turtle reproduction um, that had to be obeyed. And let me tell you something. I'm just I have a all right, y'all. I'm a level with you. I'm almost 60 years old. Gary, don't look at me like that. Gary's looking at me. You're a baby, Hakeem. But I've observed the earth over the course of my life. And, growing up in a rural part of the country, you're really in tune with the insects. And, every time you pass by some water, there's frog eggs in there. Can't tell you the last time I saw a frog egg. But, I got really uh, concerned about the lack of biodiversity, the loss of biodiversity that I've witnessed in my own life. And not to mention the different trees that we would just go and eat some stuff from. You got a few years on me. Hey, I date back 13.8 billion years. Don't make me pull out my hydrogen. So uh so I was wondering, like, for example, where'd all the plum trees go? Where'd all the pecan trees go? We had these trees, June berries, where'd they go? They're gone. We know where the stands and got them. And I thought, oh, maybe it's the loss of um, pollinators, right? But I found out a couple of weeks ago, because somebody else was standing on their soapbox, it's the loss of forest fires
Mm-hmm.
because those trees can't see through the canopy. So the fires were keeping them a spot in the forest so that they can, receive sunlight. And so what I'm getting at is that it's a tangled web of life and this appreciation we have of nature and the sky. And there's so many ways that it overlaps and so many different, the phrase geoengineering is a bad word for a good reason. But the thing about geoengineering is that you're doing it anyway. you know,
Yeah.
and it's like, oh, if you do it intentionally, there are going to be unintended consequences and things are going to go wrong. But if you do it unintentionally, there's going to be unintended consequences and things are going to go wrong. So the question is, what do we do? If it was your planet, your nation, how would you guide them? Answer that question, and that's what we're going to do.
Awesome. Well, thank you. There's another question
Yeah.
that I'm asking here from Cynthia. It says amazing information and presentation. Thank you.
Thank you.
Absolutely poetic. We wonder if you are indeed a poet outside of your work in astronomy.
I have been my whole life. In fact, I can remember one of the first poems I ever wrote. Not all of it, but I was really big into poetry. I was a depressed kid, and my mom was a reader, and so I got into Edgar Allan Poe really young. I used to actually be into Shakespeare poetry, and I also got into Rudy Ray Moore. For those of you who don't know, those of you who know, at 9 years old, I could recite Shine and Dolomite, and by 13, I also had the signifying monkey. And then I became a rapper. Believe it or
Can
not.
you give us a little sample like right
Hell
now?
no.
Come
It's
on,
different brand.
please.
Different brand. No, 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 no. Someday over a dirty martini.
You got it. Okay.
So it's funny because those who knew me, you know, uh, back when I social media, and I don't really social media much anymore, but even as far as when I was in Silicon Valley, I used to just freestyle at lunch. Then I became a grown up.
Well,
Hey, I
that's
was in
too
my mid
bad.
30s. I was in
That's
my
too
mid
bad.
30s. Yeah.
That leads me actually into my next question. Michael, do you want to hop on here and ask this yourself? Can we unmute you? I don't know if we can. I'll ask. Let's see.
All right.
Where's Michael? We gotta get Michael up here. We got another fan in the house.
Oh, okay.
Um,
Michael Reimer.
let's add Michael.
I
There he
am a
Oh,
huge.
is.
I've everything. Sorry, everyone. I'm gonna fanboy for a second here.
oh man.
I have seen everything you've done, so thank you so
Oh
much.
man.
I'm
Oh,
sorry
thank you,
for
man.
my tardiness here, but yeah, I'll thank you, Betty Maya, for letting me ask this personally. How do you, and I guess, how could we inspire the imagination and the curiosity that we see in young people, kids, about the universe? How do we foster that? And then how do we reignite that in not only ourselves, but other people, people who can
Yeah.
make the difference that we're trying to make here today?
Yeah, man. Read the room and connect with the people.
Sure.
That's the first thing, when I get with a group of people, the first thing I do is like I just figure out how to, break down barriers and create connections. But
Hmm.
like for example, remember me talking about standing outside in Mississippi looking at the night sky? All
Yeah.
right, tell your kids, put your fingers in your kids' ears right now. I'm about to say a curse word. Um, my one buddy, Jackie Pugh, he passed away a couple years ago, my classmate. And whenever everybody, we were standing there talking, I'm just looking up at the sky. And then I see something interesting. So I'm like, hey, you see right there? And Jackie, right on cue, he always he come in with, here he go with that shit again. Right? I never instilled it in the people around me, man. You gotta, you get in where you fit in, right? And it's a not a one size fits all solution, but I tell you, man, the phrase "smile and the world smiles with you," right? Like where I'm from, it's crazy how I lived in two worlds, right? Where I'm from, people looked at me as Urkel, right? And then I come into the world of physics, and they looked at me as like, uh, Tupac and Menace to Society. you know.
Sure.
And I remember my brother was like, dude, you don't fit in anywhere, right? Yeah, gangsta nerd, right? So I feel like, man, it really starts from a love of the people, and if you love it, they're gonna love it with you. But if you don't, read the room and put connection first. It's kind of like, when I talk about scientific stuff on TV and that kind of thing, I think entertainment first, not giving the information first,
Sure.
right? Yeah, and getting in people's hearts and minds is about connection, and I think that the state that you put yourself in also matters, right? And how you put it in relative to them. Uh, and I grew up in, one of the things that they stressed to me as a Southern boy, is always be polite and and self-deprecating humor and that kind of stuff, and that helps ease it, put people at ease.
Yeah.
um and 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 then when I do rob them, see, they don't see it coming, right?
They're disarmed.
They're disarmed, literally. No. But yeah, man, connect with the people, man. Connect around love, and nothing blows a mind like looking at Saturn through a telescope, right?
Right. It's the same reaction every time.
Every time, yeah.
That's all I have. Thank you very much for being here. I'll
Thank you.
go back
Where you
off.
based,
I'm
Michael?
in Denver,
Oh, you're in
but
Denver.
but
Oh man.
yeah, from Dallas, Texas. So I kind of
Okay.
get a little bit of the southern kind of
Yeah. Yeah.
culture that you're talking about there.
Right. Right. Oh, it's culture-y. It's
Culture is a word.
But where ain't, man? I lived in Boston for a year and a half. It's culture-y.
There you go.
Where I live in now, Northern Virginia, DC area. Yeah, it's hard to pin down the culture because I
Right.
think there's so many different people from so many different places, which could be the culture, like the San Francisco Bay Area, right? That is the culture.
Yeah.
Yeah.
Cool. Thank you so much. I'm gonna disappear off mute now, but Betty Maya, back to you.
Hey, you bought my book? You bought my book?
Not
Mike?
yet. Not
Not
yet.
yet. I didn't say read it.
Oh, that's for I can buy books all day long.
Yeah, so Michael just recorded a wonderful piece with More Than Just Parks that we shared on our social media.
I'll check it
Michael, maybe
out.
you can put the link in the chat. He did an awesome narration, and like I've
Ooh.
just been imagining both of you guys doing some narration together someday because you both have awesome voices and smooth,
Hey, I
like
love to
I would want
create.
to listen to both of you all day long. So check out that narration. Maybe we can
I'm with you,
do
Natasha.
some together in the future. Okay, there's one question I want to ask from Todd, who is here as well, our Minnesota Starry Skies North on the
Ooh.
board chapter leader there. And he asked a very scientific question. So we're going to get a little scientific. Todd asks, if Earth's protective magnetic field is due to the cosmic accident of the collision with Theia, does that suggest that the likelihood of life on the surface of exoplanets is lower since they're less likely to have a protective magnetosphere?
Yeah, yeah. Well, what? So here's the thing that is weird about our solar system is that if you look at that list that I put up, that plot with the four different types of planets, you had terrestrial planets, of which is tiny percent like Earth. Then you had more gas giants like Jupiter, Saturn, ice giants that they call Neptune-like or ice giants. And then there was a category called super Earths, right? That were just as abundant. So we have the gas and ice giants and even the rare to find terrestrials, but we don't have a super Earth. So if you look at, for example, Mercury, Mercury is pretty much a giant chunk of iron with a little crust of rock. you know, there's different planetary configurations that might exist. And so the geology of a super Earth, like the variation in what the interior might be like, it could be much different. And you would expect a fast rotating super Earth. Uh, you know, the question becomes the core is not going to cool so fast. So it's not going to Mars out on you. So you're going to have you could be able to maintain a current for a longer time. You're going to have more, decaying radioactive products. You're going to have more residual thermal energy. Um, so I don't think it's that cut and dry, I guess is what I'm saying, right? Because there's
Yeah.
so much variation in in one of the most common planets in the universe, we don't have it. Like, how can we, that I got to look up simulations, which I haven't. Thank you for giving me that. So I will do that. Look up simulations of what terrestrial planet interiors are like. I mean, not terrestrial planet, super Earth planetary interiors are like, and what their magnetospheres may be like.
Yeah. Well, we are about out of time. I want to read this comment from Kathy Hansel, who's our San Diego chapter leader, who says, "What a wonderful way to wrap up International Dark Sky Week. Thank you all, very educational. Dr. Oluseyi is such a down-to-earth scientist, making it interesting and understandable rather than intimidating." So yes, I agree. This has been a
Thank you for the
dream come
love.
true for me. Thank you so much. We're all huge fans here, and I think we'll all buy your book. So,
It comes
yeah,
in two types: young adult and adult.
nice. I'm gonna get the young adult one. I've been really into young adult books recently.
Well, you're this is a blood, sweat, and tears story. I mean, I
Okay.
had quite a
I
rough
bet.
life, and
Yeah.
they got rid of a lot of that in here. In
Okay.
fact, the book was 50% thicker when I first wrote it, and my uh my editor was like, Hakeem, at this point, you're abusing the reader. You can't,
Oh.
you know, you don't have to tell
Well,
them about every.
can you bring that up and show it on the camera again and tell us the title and where we can find it if you have a suggested place?
The title is A Quantum Life: My Unlikely Journey from the Street to the Stars. And you can find it on Amazon. And for bookstores, I did read the audiobook myself.
Nice.
Yeah, I'm actually
Okay.
here's another piece of trivia. I'm a trained voice actor, and I did a lot of work for guess who back in the early 2000s, MTV. So if anybody ever watched Radio Sonic Net, and remember Sonic Net, baby, that was me.
I think that was maybe a little before my time, but I will be looking that up.
Why I gotta do that for me, Betty? Ye of the 21st century.
Yeah. No,
Betty
I'm
Mai
from
of the
19th
21st century.
century, I'm from the 19th century.
Ah, okay.
No, I don't know. I'm from the 1900s. I'm from the
Hey,
1900s.
I'm half Time Lord, half human, half Vulcan. So, be
Oh, that
anyone
is,
can have it.
can we please mind meld?
Well, I don't quite trust you yet. So I'm gonna
Okay,
like Vulcan
okay,
pinch you first, then mind meld.
okay. All
Uh,
right, deal.
See, y'all just let that slide by. Did you not catch what I said? Half human, half Vulcan, half Time Lord.
I don't know what Time Lord is.
Doctor Who.
See, Michael,
And
sorry.
the thing is you can't have three halves, right? And the thing about Time Lord technology is that it's bigger on the inside than on the outside, just like a black hole. So I can be three halves and be one because of the Time Lord inclusion.
Cool. Okay.
That's what I was
We need
getting
to
at. That's my
rectify this.
complex third humor.
All right. Well, thank you.
Thank you guys.
150% of you. We appreciate
Some of us
your,
got it. Thank you,
your,
Elisa.
your time, your lovely self, your knowledge, and your passion today. What an incredible way to celebrate International
Thank you
Dark
guys.
Sky Week. Thank you. Would you like to share any last words? Maybe some words of like advice or support for
Mhm.
people, for all of us here who've been fighting to protect the night, that
Mhm.
any words to keep us going and keep us inspired on our journeys?
Listen, like I said, my journey through life has been completely unexpected. And for some reason, I don't know why I was born with, and I guess we all are, right? Homo erectus went around the planet, evolved into sapiens. We are amazing. Just the fact that we hunt other animals by just running longer than them, right? That's how I got a football for my 6-month-old dog last week, right? I outran him till he got tired and had to put the football down. It's a nerf, so he's going to chew it up. You can do just about anything. Just stick with it. And magic moments occur. and you take more losses than you do win. So, for a lot of my life, I said, I don't know if I'm a loser or I'm a winner because I've lost way more than I win. But you external humans only see the wins, right? You only pay attention to the wins. I know and feel every loss, right? And you're in that same position, right? And I think that um, I realized many years ago that for the most part, it's going to be okay, you know. And I tell you this, I don't know if you guys think about time, but I was having this thought many years ago about Rocky Cobb, the physicist, told me that apocryphal quote from Mark Twain, which is that he applied it to the universe. When it comes to deep new insights, like say Einstein or Galileo or Newton, um, it's not what you don't know that gets you in trouble; it's what you know for sure that just ain't so, right? And I started thinking about what do I know that just ain't so, and I started thinking about time, and I started thinking about how we're sharing this moment that we call now, but you need pressure bulkheads to hold pressure, ain't that right? Uh, but every conscious being has thought that, right? So what makes our now the now? And it seems like all timelines are co-equal. And what that means is already a billion years from now, and I'm already dead, right? And so,
Yeah.
that was for me a really freeing thought. A lot of I never had much embarrassment in my life anyway. In terms of feelings, right? My mom, when I was a kid, she had this book titled Your Erroneous Zones, and it was about emotions that don't do you very, don't serve you well. And one of them was embarrassment. I was like, hey, you got a point. So I trained myself to not be embarrassed, just live, right? And I think that as you stay on your mission, you need some perspective like that, right? The story's already told. You've already done it, right? You've already succeeded. You just got to go through it and keep up the good work, right? And in the end, it works out. And I find that we're in a time now of, hey, look at me, and virtue signaling and all this
Mm.
sort of stuff. But the traditional values of honor, duty, man, I still stick with them, right? I'm like, man, I'm like, I imagine sometimes, what if I had cursed one time on social media? you know, they would have got me. Um, but if I think if you stick to those fundamentals and you keep your belief and faith, and that really it's all going to work out, and you just move forward, then it comes. And I tell you, in my life that I've lived, you know, um, applying for proposals, I get a tiny percent of the ones I apply for, but yet, that means I just got to apply for more, right? It's that kind of calculation in every stage in life. When people ask me what I do, I used to say I'm a science mercenary, but then people kept pointing out the negative connotation of mercenary.
Yeah.
Uh, and so I started saying I'm gonna make it happener. That's what I do, right? And so I don't live in comfort. And what I mean by that, as an expert, you're expected to be the expert on the thing. And so you become an expert young, you stay doing that thing for life. And that's never worked for me because I just get bored. And so always being the new guy in the world of experts, always trying to make a new contribution, even going into places like I do this TV stuff, man, sometimes I've shown up in these, when I show up for a science TV interview, they're like, ah, good looking guy, nice voice, smart, great. I show up one of those regular Hollywood videos and I look around the room, I'm like, holy hell. Am
Yeah.
I the only one who wasn't made in the lab?
Yeah.
Yeah. But it's gonna be okay. You don't get those opportunities, but then you get the other one happens, right? So just stick with it. You got it. You got it. I mean, that's just it.
Nice. Well, that is beautiful and a lovely cosmic perspective to send us all away. Thank you, Dr. Hakeem Oluseyi. Idol, thank you for being here. Seriously, one of the coolest humans. This was such a joy and a pleasure for me to
Thank you
host
guys.
you, to host all of Dark Sky Advocates here today. You can revisit this immediately. It's on our Facebook page at Dark Sky, and we will be also posting this to our YouTube channel. And yeah, how can people get a hold of you? Do you have social media? Do you is
Yeah,
there
so I'm on Twitter and Blue Sky. I'm on
okay.
LinkedIn. And astrophysicist.org is the organization I work for right now. The IMAP satellite is it's based out of Princeton. Dave McComas is the principal investigator. Awesome guy. So I love working, I curate my people That's the other thing about, enjoying life. People are your greatest asset, but they're also your greatest headache, right? Unless you have a puppy. And so
Yeah.
yeah, and so astrosociety.org, and the
Great.
IMAP satellite. Oh, and I have a podcast, but it's in collaboration with Roddenberry, the founders of Star Trek. It's called Does It Fly? So it's about science fiction. And so my co-host is a woman named Tamara Krinsky. She's Marvel's red carpet host, but also a writer and just another brilliant person. And when I say another, I don't mean in addition to me. I mean in addition to all the other brilliant people.
No.
And so we evaluate the different conceits in different sci-fi franchises, and I evaluate them for the science, right? So, for example, we just did the Death Star. So, what does it take to build a Death Star? Look it up on YouTube. Look, the podcast ain't a failure. When you look at YouTube, see we get 150, 200 views per episode, but our main distribution is through Den of Geek. And so through Den of Geek, we get over 100,000 viewers per episode pretty quickly. And they're our partner. So denofgeek.com, I guess, is their website. Our podcast is at doesitflypod.com, and Does It Fly everywhere else.
Cool.
Oh, somebody put it in there. Thank you, Diane.
Diane popped it in the link. Diane is amazing.
Yeah.
Well, she's in
Oh
Pittsburgh.
man, and let me tell you guys, I just found out I recorded a show last fall with a beloved A-list Hollywood person. And I just found out that it's too expensive, so the network might not make it. But oh, you guys would have loved it. Let me tell you.
Well, can we we'll sign a petition, like we can circulate some.
Man,
you have the Dark Sky Network on your side for support.
I had to do a stunt. I literally did a fall off a building, like
Mythbuster style,
like dozens of feet fall,
fly.
like dozens of feet actual fall.
Wow.
Like, yeah.
That's terrifying.
You're telling me. All right. Take care.
All right. Thank you. Happy Dark Sky Week.
Bye-bye.
We'll see y'all soon.